Our lesson on 2.4 and 2.5 is going to start off talking about right triangle trig applications, which is something that'll be a review from geometry and from Algebra 2. But then we're going to get into things called bearings and true course, and they do get a little complicated. So this is a really long lesson, and when it's actually taught in the classroom, this is taught over several days. But if you miss the entire thing, you're going to have to start at the beginning. So first, section 2.4 applications. Find the page of your notes that looks like this. And it says if two equal sides of an isosceles triangle are 24 centimeters, the two equal sides are 24 centimeters. If each of the two equal angles is 52 degrees, find the length of the base and the altitude. So they've labeled the base as, half of the base as y. We're going to have to figure out the whole base in a minute. And then the altitude as x. So when I look at just this triangle right here, lovely. Here's my angle of reference. In order to calculate the value of x, I could use the sine function because I would have x as the opposite and 24 is the hypotenuse. So we could set up the sine of 52 equals x over 24. So on your calculator, make sure it's in degree mode. You're going to do 24 times the sine of 52. And when you calculate that, you get 18.9 centimeters. So there's the altitude of our triangle. Now we're going to do something similar to find the value of y, and then once we know y, we can double it to find the whole base of the triangle. I think I'm going to set up cosine this time because I have adjacent as the y value over hypotenuse. So on your calculator, you're going to do 24, that's cosine of 52. And then if you type that in, I think you get 14.8 centimeters. Now, that doesn't necessarily mean that the whole base of that triangle is 14.8. The base of the triangle is going to be 14.8 times 2, so 29.6 centimeters. Alright, so that should be very familiar from your geometry and Algebra 2 life. So a couple of definitions that we need to think about. If you have something called an angle of elevation, usually this is from a point on the ground, and you would be looking at the horizontal, and then if you look up, that's called an angle of elevation. Now, if you are at the top of a mountain, a cliff, a lighthouse, a plane, and you look out at the horizontal, and then you're looking down at the ground, so the ground would be down here, that's called an angle of depression. And we're always going to consider these things to be positive angles, but sometimes the angle of depression is not actually in the triangle that we're trying to talk about. So this example in particular has a really cruddy picture, but they do show you that the angle of elevation is down here. If I read carefully, it says the flagpole is 75.0 feet. I'm not too worried about sig figs in this unit, so don't worry about it if you forget to round to the appropriate sig figs. Just don't round too much. So the flagpole would be this vertical component, 75. The shadow is on the ground, and that's 43, and they want us to calculate this to the nearest 10 minutes, what theta is. So, looks like we have the tangent ratio. So tangent of theta is opposite over adjacent. So on my calculator, to find theta, you do the inverse tangent of 75 over 43. Now, because they want to the nearest 10 minutes, you're going to have to do some calculating conversions, and I can't grab my calculator right now, so I'm just going to trust that y'all remember how to do this. Theta comes out to 60 degrees, and then the decimal component, when you change it to minutes, comes out to 10 minutes if you round to the nearest 10 minutes. Kind of a strange way to round it, but just do what they ask. Okay, the next example has a man who's climbing up 213 meters on the side of a pyramid. Finds that the angle of depression to a starting point is 52.6 degrees. So here's the side of our pyramid, and here he is up here, and this is our starting point. So he climbed 213 meters distance. His angle of depression would be this angle looking down at the ground is 52.6 degrees. I'm going to kind of arrow that in here. And the question is, how high off the ground is he? So they want us to calculate this value right here. So with this information, I think I can set up a sine problem. The sine of the angle, which is 52.6, is opposite over hypotenuse. So on my calculator, 213 times sine of 52.6 is 169.2 meters. And please pause, rewind, whatever you need to do to understand how things are typed in your calculator. Okay. What probably happened in class is we continued to talk about right triangle applications at this point, but I'm going to give you an introduction to bearings right now. This will not be the last time you see this bearings concept, because we're going to have about 3 pages of notes that covers both right triangle applications and then a bearing application. So a bearing, they have a definition on your page of a line, is the acute angle formed from the north-south line, and the notation used to signify it begins with either north or south. So we always measure bearings off of either the north or south line, and sometimes we actually have problems where they assume that you're measuring off of the north line every single time. So when they say you have a bearing north 40 degrees east, that means off of the north line in the east direction you have a 40-degree angle. So that would be the bearing of this particular line. This particular line is north 65 degrees west. So off of the north line, heading in the west direction, you've got a 65-degree angle. This bearing is south 70 degrees east. So from the south bearing, from the south axis, you're going to measure 70 degrees in the east direction, and that is the bearing of that line. And then south 20 degrees west, go in the west direction from the south line. That is the, whoa, that is the bearing of that line right there. So we're going to have an example of San Luis Obispo, California, is 12 miles due north of Grover Beach. Arroyo Grande is 4.6 miles due east of Grover Beach. What is the bearing of San Luis Obispo from Arroyo Grande? So let's draw ourselves a little picture. So San Luis Obispo is 12 miles due north of Grover Beach. So let's say this point right here is Grover Beach. And then 12 miles due north of him would be San Luis Obispo. Then Arroyo Grande is 4.6 miles due east of Grover Beach. Now, obviously not drawn to scale at all. The question is, what is the bearing of San Luis Obispo from Arroyo Grande? So, they want us to basically calculate, Arroyo Grande is your beginning point, so we're going to think of that as our axis. So from our north-south line, they basically want us to come up with this bearing calculation from here to here. Well, this wouldn't be a very difficult question if I did a little bit of trig to start with. Remember, this was a 12 and this was a 4.6. So what I would like you to calculate is how big this angle right here is, theta. So we can do that using an inverse tangent. And I didn't calculate this one yet, so let me grab my calculator. Looks like it's 69.03 degrees. So we'll just say 69.0. So we want to do this angle off of the north line. So remember, from the axes on the west coordinate part to the north, that would be 90 degrees. So 90 minus 69 would be 21 degrees. So this part right here, I'm going to mark it with green, is 21 degrees off of north. So the way we say that is from north, we move 21 degrees, and then it was towards the west direction. So, and you have to read really carefully. At first when I did this problem, I actually went from San Luis down to Arroyo Grande, but that's not what they wanted. They wanted our starting point to be at Arroyo Grande. Okay, a boat is traveling on a course of bearing 52 degrees 40 minutes east, north of east, for a distance of 238 miles. How many miles north and how many miles east has the boat traveled? So, first thing I want you to do is, here's your boat, starting point. And since that's our starting point, I'm going to kind of draw in a little axis. I'm going to draw on my bearing line 52 degrees north east in direction. Okay, so approximately like this. So in the east direction off of north, this was 52 degrees 40 minutes. And it was for 238 miles. And the question is, how far east and how far north has this guy traveled? Well, his east and north directions would be perpendicular to one another. East I'm going to call X, and north I'm going to call Y. I think we have a trig problem. Now, part of the issue is we need to calculate this angle right here by saying 90 minus 52 degrees 40 minutes. So remember, on our calculator, you can either change it to 52 degrees and 40 minutes using your symbols, or you can say 52 plus 40 over 60, and you're going to get a decimal degree, and that's okay. So it's 37.33 degrees in that little corner. So right here is 37.33. And now to find x, I could set up a cosine problem. So cosine of 37.33 equals x over 238. And then to find y, I could set up a sine problem. So sine of 37.33 equals y over 238. So cross multiplying for my x direction, I think I got 189.2 miles. And that was east. I want to be as specific as possible. And then for my y direction, which is north, I got 144.3 miles north. Okay. Let's keep going. Now, somewhere else on your notes, you have something that looks like this. Trig notes 2.4 and 2.5. Reviewing the concept of angle of depression and elevation. Sorry, the bell's in the background. Angle of depression is off of a top of an object down to the ground. So this is an angle of depression. He is the same value as the angle of elevation. So if you're at the top of a tree looking down at me and I'm looking up at you, we're actually looking at the same angle. So they're going to show you here that we've got a couple of buildings here. It's kind of a confusing drawing. But let's look at our first example. And it says page 92. I'm not sure if that's for our book or if it's for the old book. To measure the height of a flagpole, Donna finds that the angle of elevation from a point 24.73 feet from the base to the top is 38 degrees 12 minutes. So here's our flagpole, and she's far away from it, and we're measuring to the top. So it is 24.73 on the ground, and the angle of elevation is 38 degrees 12 minutes. That's an 8. And they want to know the height of the flagpole. So this is, again, is a right triangle. So we can set up, let's see, tangent. And then I always try to turn them into fractions, even though I know you have a minute symbol on your calculator. It's up to you. 4.73. So cross multiply on your calculator, and I think we get, let's see, 19.46 feet. Alright, next example. Find the angle of elevation of the sun if a 48.6 foot flagpole casts a shadow that is 63.1 feet long. So we got this flagpole again. And the angle of elevation would be from the ground up to the sun. So the flagpole's here, you know, your sun's somewhere up here. There's the sun. And he's casting a shadow on the ground. So the shadow is 63.1 feet long. The height of the flagpole is 48.6, and the angle of elevation we don't know. So again, we're going to set up tangent, but this time because we want to know the angle, we're going to use the inverse tangent of 48.6 over 63.1. So on my calculator, I think I get 37.6 degrees, and it doesn't say how they want their answer, so we're just going to leave it like that. Okay, back to the idea of bearings. Sometimes if they don't specify, north 32 degrees east, they're going to assume that we always go off of a north line. So if you notice that your bearing is a value that is greater than 90 degrees, or if it doesn't specify east or west, you always go off of north and you travel in a clockwise direction. So these are some examples of what bearings would look like in that notation. 40 degrees, 164 degrees, 230 degrees, and 308 degrees. Let's look at some other examples of how we can label these. So, this particular example, let's go back to our old notation. 38 degrees this direction. So off of north, you travel 38 degrees east. Now in that new notation that we just learned, they would have just called it 38 degrees with the understanding that you came off of north. Now this is the south line for this example. So we start off the south line and we're going to travel 42 degrees east. Okay, this example, this is off the south line again. So south, and you're traveling 29 degrees. This time we're going west. And then this got kind of cut off, but it's off the north line. So from north, looks like we traveled 52 degrees west. Okay, some examples now. We have radar stations A, I think that says and, B are on an east-west line 3.7 kilometers apart. So here's A, and here's B. And let's see if my drawing can even look close to right. This is 3.7 kilometers apart. Station A detects a plane at sea of a bearing of 61 degrees. Now since they don't specify north, south, east, west, we're going to assume it's off of the north line. So I always like to draw a little coordinate here, and if I go 61 degrees off of the north line, that would look something like this. So this is a 61 degree angle right here. Then station B detects that same plane, but he's at a bearing of 331. So again, we're going off of his north line. So 331 degrees, let's see, that'd be 90, 180, 270, so somewhere up here. Oh wait, pretend that connected. Now, if this was 331 degrees all the way to here, we got to think about how big the angles are in the actual triangle. Turns out in this class, every bearing question we do will always form a right triangle. So we're going to assume that this is at a right angle, but we could prove that pretty easily. For instance, if this is 270 up to here, and remember we went to 331, that would make this a 61 degree angle. Right, what was I saying? Right here. And then, remember this is a right angle from here to the east line. So if this is 61 degrees, that means this is 29 degrees. And then triangles have to add up to 180, so that would force that to be a 90 degree angle. So what do we need to know? The distance from A to C, and this was C up here, by the way. So if I'm trying to find this distance right here, and this is a right triangle, you can go from whatever angle you want. I'm going to go off of this angle, and I'm going to set up a cosine ratio, because I have this side adjacent to him is what I want, and I have the hypotenuse. So on my calculator, 3.7 times cosine of 29 gives me 3.2 kilometers. Now, if that was confusing, you need to stop, rewind, and watch that one more time, because these are not easy. Okay, we kind of have a half of a diagram set up here. The bearing from A to C is 52 south, 52 degrees east. So this must be C down here. But off the south line, it measures 52 degrees east. So that's a 52 right here. The bearing from A to B, this must be B over here, is north 84 degrees east. So that would, from A to B would be north and then 84 east. The bearing from B to C is off of south and it's 38 degrees west. And a plane is flying 250 miles per hour, and then it tells us for 2.4 hours. Now that's a little bit of a problem right here. We need to multiply 250 miles per hour times the 2.4 hours, rate times time, and that gives us our distance, which apparently is 600 miles. because the number you want to put on your triangle is actually distance. So distance here is 600. The question is, how long is it from A to C? Okay, well, let's fill in some things that we can calculate. From here down to the south line would be 180 degrees. So if I do a little subtraction, 180 minus 84 minus 52, I'm going to get a 44 degree angle right here. And I think I have enough information now to go ahead and find this answer. If I take it from this angle, remember these are always going to be right triangles. You can prove it's a right triangle pretty quickly, but trust me for now. We can set up, let's see, cosine of the 44 degree angle would be adjacent over hypotenuse. So on my calculator, you get 431.6 miles. So once you get the picture drawn and labeled, it's not that bad because you guys are really good at setting up trig ratios. The next section I want to talk about involves what's called true course. So go through your notes, like I am, and try to find the part of the notes that is titled 2.5 true course. Alright, so the bearings idea still applies to what we're about to talk about. A boat is crossing the river that runs due north. So the heading of the boat is due east, and it's moving through the water. So the boat, what's happening here, here's your boat. And he's trying his best to travel across the river east. But because there's water pushing on him, he actually ends up kind of going diagonally across the river. He'll eventually get to the other end of the river, but it's going to take him a little longer because instead of going due east, he's going to kind of get pushed up on a diagonal. And the water is moving at 12 miles per hour. The current of the river is a constant 3.25. Oh, the boat was going 12. The constant is 3.25 miles per hour. Find the true course. So basically, we need to figure out at what direction he's traveling and now at what new speed. So we're going to do this by using a tangent function and a little bit of Pythagorean theorem. So let's see. Oh, I need to back up. I really need a new slide in here. So let me just kind of, sorry, I'm fudging this a little bit. Let me erase that. Okay. So what we're going to look at is if I could find theta by using inverse tangent. That's pretty easy to do. So inverse tangent of opposite over adjacent. And on my calculator that comes out to, let's see, 15.2. Now, that is not the actual bearing of the boat. Remember, that is just the angle right here. Oops, that's a 2. I can read. They want us to come up with the bearing, which is this guy right here. So if we measure it off of the north line, remember from here to the east line would be 90 degrees. So find his complement, and that'll be our actual bearing. So that is his bearing off of north. We're going to measure these off of north because it's just kind of easier. And then to find the actual speed, what we can do is we can do Pythagorean theorem with the 12 and with the 3.25. Now, they didn't really tell us time at all, so I'm just going to assume they went for 1 hour. So Pythagorean theorem says 12 squared plus 3.25 squared would be, and if I square rooted it, that would be my hypotenuse, which is t. So on my calculator, that comes out to approximately 12.4. And then we're going to label that as our new rate. So our boat is really heading in a very different direction than it intended. So the true course is 12.4 miles per hour at a bearing, and you can either say north 74.8 degrees east, or if you just said 74.8 degree bearing, I would understand that that meant off of north. Okay, let's look at another example. So we've got a plane that has an airspeed of 195 miles per hour and going 30 degrees. So again, we're going to assume that means off of north. We've got air currents that are moving at a constant 32.5 miles per hour in a different direction, 60 degrees west of north. find the ground speed and the true course of the plane. So first thing they drew for you up here was the plane itself. So 30 degrees would be traveling in that direction. So this is where your plane's actually going. Or at least it's intending to go that way at 195 miles per hour. Now, because the course of the plane is being affected by the wind, off of the tip of that, what we would later call a vector, we're going to adjust it with the wind. So remember, he was 60 degrees west of north. So off of north, measure 60 degrees west, and then here's the wind affecting it. So what we are now going to find, if you connect these vectors, is the true course. So they kind of have drawn the picture over here. The 32.5 is this leg. The first thing we need to do is find theta, and we can do that pretty easily by using, let's see, this is opposite and hypotenuse, so we can use a sine function this time. Oh, no we can't. Silly Bruzo. Back up. I did not draw this right. It's a little confusing to see what's going on here, but if you think about alternate interior angles from geometry, this north-south line and this north-south line, whoops, are parallel. So if this is a 30-degree angle from here to, here, then this also has to be a 30-degree angle. Picture's not drawn real well, so I apologize. Now, if these three angles added together would have to be 180, so it already is 90, which means this right here has to be the 90-degree angle. Let me erase that a little bit so we can see what's going on. Okay, now we're going to use the inverse tangent function. That makes a lot more sense to me, to calculate what this angle right here is. So inverse tangent of opposite, which would be 32.5, over adjacent, which is 195. And for that, this is theta, by the way. For that, we get, let's see, 9.5 degrees. Again, not drawn to scale, so don't get offended by this drawing. Now, we actually only need to find the bearing, which is from the north line to this new line of the plane. Because remember, this is what the plane intended to go. This is the wind, so this is what it actually is traveling. So, if I knew it was 30 degrees from here to here, I need to take away the 9.5 degrees from theta. So the bearing is 30 degrees minus the 9.5 degrees. So the bearing is actually a 20.5 degree from north. And then the true course, the t, is just going to be Pythagorean theorem. So again, quickly calculate it. This is t. And when I do that on my calculator, I think I get roughly 198 miles per hour. So the true course of this plane, true course, is 198 miles per hour at a bearing of, and you can either say from north, we're going 20.5 degrees east, or you can just say 20.5 degree bearing, and we will assume it's off of north. Whoops, going in that direction. I know that was really kind of gross and really kind of ugly. I think it kind of made it worse because the picture we have wasn't drawn all that well. So what you might find, and I'll do this even in our lessons and our notes, if I don't like my picture because it's not looking to scale or it's not nice enough, I will just go ahead and redraw it. And I know that sounds shocking coming from me since my pictures are always disgusting. Alright, let's talk about vectors now. You're going to enjoy vectors because they're a little less complicated than what we just covered in bearings. So find your notes, it talks about vectors. And a vector has both magnitude and direction. And that's what makes a vector kind of special. So it tells you how big the vector is, size-wise, that's magnitude, and then what direction it's actually traveling in. So a car going in two different directions would give yourself two different vectors, or in that case I gave you three different examples. Now notation's a little strange. The notation for a vector would either be a capital letter, a letter with like a ray symbol over it. It could be two letters like a ray in geometry. The x is just a scalar, and then when there's absolute value bars around a vector, that actually means the magnitude, so the size of the vector. The quality of vectors, you can add vectors, you can subtract vectors, you can do all sorts of things with vectors. So first, the addition of vectors would be, here's vector u, and then if this was vector v, you would attach the tip of the first vector to the tail of the next vector, and then connect the beginning and end points, and this is your new vector, which is the sum of u and v. And you notice it made a parallelogram. They kind of drew that in with dashed lines. The next example, by the way, we could label this. The next example has vector u and then vector v being added in figure 4. If you notice, if this is vector u, this is also vector u, and if this is vector v, this is vector v. You don't have to get deep into vectors for this course. When it comes to drawing the vectors, we just have to know how to apply them in our applications. Let's see. So in this case, the vector would be down the middle. And then this is the subtraction of the vectors. So here's vector u, and then to attach tip to tail, when it's subtracting vector v, he's going to go in the opposite direction of what he used to go. And then you're going to get a resultant vector, u minus v. Again, you don't need to worry about this so much for this class. Here's a problem, and it gives you the boat, kind of like the one that we saw in another set of notes. And the boat is crossing the river that runs due north. So here's our river's current going due north. The boat is trying its hardest to go east, but because of the river, it's going to be pushed up onto the diagonal. Find the true course. So first thing I think we need to do is realize this is a right triangle. Let's go ahead and use the inverse tangent. Now they called this theta. I'm going to actually switch this and call it beta, because for bearing. Let's find this angle right here. So we could use an inverse tangent function of opposite over adjacent. So theta, let's see, I think I calculated this already, came out to 23 degrees. But that's not our actual bearing. Our bearing, because it's off of north, is going to be 90 degrees minus the 23 degrees. So that gives us 67 degrees. So that's our actual bearing. And it's off of north. Now we're going to do Pythagorean theorem to find the length of the true course's vector. Let's see, 12 squared plus 5.1 squared comes out to roughly 13 miles per hour. So our true course, just like on the last section of notes, is 13 miles per hour. So the boat is going a little bit faster because it's being pushed by the water at a bearing. And you can either say at a 67 degree bearing or 67 degrees east of north. Alright, and I rounded it to 13 because it said 2 significant digits. I don't think it came out to exactly 13, I forget. Okay, so this is where they're talking about possibly calculating it off of just the north position and going in a clockwise direction. So just remember that there's 2 ways that we can signify bearings. This example has a plane that's flying at 170 miles per hour with heading 52.5 degrees. So this is the plane, this is the intention. This is what they wanted to fly. Unfortunately, there's a wind. So this is the bearing of the actual wind at the tip of the plane's route. And he's 35 degrees, or 35.0 miles per hour at 142.5 degrees. So you'll notice the wind, his bearing measures off of north at 142.5 degrees. Now this 52.5 is filled in because of corresponding angles. So if this is a 52.5 degree, so is this, because the plane has not changed direction in its intention at least. When you look at the wind now, we need to think about where, let's see, picture's all labeled. They want us to find the ground speed and true course of the plane. So basically we need to find the angle of how the plane is actually traveling, and then also how fast it's going. So first, let's go ahead and find the x, because that seems a little easier to me. So Pythagorean theorem. So we're finding the true speed of the plane. So let's see, this is a 90-degree angle. If you thought about why it's a 90-degree angle, that has to do with all your geometric properties, which we could go over, but I just don't have time. Okay, square root 170 squared plus 35 squared. Oh, looks like approximately 174 miles per hour. So that's this guy. And then, let's see, we need to find theta, and we can do that using our inverse tangent. So theta is the inverse tan of 35 over 170. So theta, let's see, I already calculated that, is 11.6 roughly. Now, to find the actual course of the plane, because remember, this is what's actually happening, is this vector right here. We need to figure out his total angle for his bearing, so 52.5 plus theta. So his bearing is 11.6 plus 52.5, which is 64.1 from north. So his true course is 174 miles per hour at a bearing, and you can just say a 64.1 degree bearing. Bearing of, if you decided to say north 64.1 degrees, let's see, east, that would work too, means the same thing. Alright, as you can imagine, what makes these kind of difficult for bearings is the pictures. If they give you a picture in the book, you do a little happy dance, because that means you don't have to come up with the picture. Sometimes the pictures are so ugly when you create them that they really just do more than, they really just confuse you. They don't really help at all. But you have to draw a picture because there's no way to set these up without a picture. Now let's talk about horizontal and vertical vectors. So v sub x is known as the horizontal vector, and he is calculated. This is just one example of what they did here. You take the magnitude of the vector times the cosine of the angle theta. And these are all things you're going to do on your calculator, so there's nothing you really need to know other than the formula. Your horizontal vector, that was your horizontal vector. Your vertical vector is the magnitude of the vector times the sine of your theta. So again, these are all things you're going to do on your calculator. So they want us to find the horizontal and vertical vectors of this human cannonball. So the horizontal vector is, remember, it's the magnitude, which in our case is 50. Horizontal is cosine of your theta, which is 60. So you could either type this on your calculator, or maybe you know what the cosine of 60 degrees is from your unit circle work. But if not, let's see, that's 25, and then it's going to be miles per hour. Now your vertical vector, still your magnitude is 50, but this time it's times the sine of 60 degrees. And if you calculate that to 2 sig figs, it's roughly 43 miles per hour. Alright. An arrow is shot into the air so that its horizontal velocity is 25 feet per second, and its vertical velocity is 15 feet per second. Find the velocity or the magnitude of the vector for the arrow. So they're kind of working backwards this time. I'm thinking if we wanted to find v, we could just do Pythagorean theorem, because remember this is 15. So 15 squared plus 25 squared is the magnitude. Let's see here. So I think that comes out to 29 feet per second. I think that is an approximation. But we also need to know theta, because the velocity, we're going to have to, well, maybe we don't need to know theta, but we could find theta really easily, actually. We just use an inverse tangent of 15 over 25. This is to find theta. So, turns out it is 31 degrees, roughly. So the arrow is shot. If they gave me like a question where I had to come up with the how the arrow was shot very specifically. For this particular example, I would say the arrow was shot at 29 feet per second at a 31-degree angle. We may have answered too much for that problem, but that's okay. It's good practice. Okay, we are back to a bearings looking kind of problem, except they're specifically talking about vectors in terms of the horizontal and vertical distances. So a boat travels 72 miles on a course with direction 27. So here's the starting point, and here's the boat traveling 72. And then it changes course and goes 37 more miles, but now it's at a new bearing of 55 off of north. So how far north and how far east has the boat traveled on this 109-mile trip? So basically, we need to calculate I didn't do this yet, apparently. So we're going to have to calculate. This might not even be your notes, actually. So if this is not in your notes, just go ahead and skip this part. But we can do this. All right. We can calculate this component right here because he's going to be the horizontal vector of this initial travel. So remember, he's going to be, I'm going to call him u sub x, the magnitude, which is 72, times the cosine of my angle, which is 63, because remember the 27 degrees off of north, we want his complement, that's the theta. So, I guess I should have done this ahead of time, but if you grab your calculator and type it in, looks like u sub x is 32.7 miles. Hold on to that for a second. And then we're also going to have to calculate v sub x, which is the same thing as up here. So v sub x is, let's see here, his magnitude is 37, and then cosine, this time the angle for this new trip is 35 degrees. So 37 times cosine of 35 is 30.3 roughly. So my total east direction is 32.7 plus 30.3, which I know I should be able to add, but I can't anymore. So it comes out really close to 63 miles east. Now we're going to do the same thing for the vertical components. So u sub y is still a magnitude of 72, because that was this part of the trip. And then times the sine of 63. And then we're going to do the same thing for v sub y for the other part of the trip. His magnitude was 37. And then for the vertical part, it's the sine of his angle was 35. So let's go ahead and calculate that. Okay, first one looks like 64.2. 21.2 for the other one. So my total vertical vector, vertical components, when I add those together, is 85.4 miles north. That was probably more fun than we wanted to have, but that's okay. Alright. And I know these problems are not in your notes, but if you feel like doing these, you go right ahead. For the sake of my voice and my time, I'm going to end it here.